Hi everyone. So sorry to be missing you today. Just not feeling too well. So we do need to move on to a new lesson today though. So I've put together a quick video. Honestly, this video goes a little bit off the cuff. I don't have your specific notes in front of me, so it'll still cover all the same material, but it might not line up perfectly with the examples and everything. Just make sure you get this stuff down. I think you'll catch on pretty quickly. So today we're talking about something called a probability distribution, and this is where we're moving back into the land of algebra. But first, to understand what a probability distribution is, we need to understand the concept of a random variable. So here's a definition for you. So a random variable, here's your definition, is when you have numerical outcomes of a probability experiment. So you can work with them numerically. So like for example, when you roll a die, just a single die, your possible outcomes are 1, 2, 3, 4, 5, 6. Okay, so in that particular situation, we could say these are values of the random variable. And you'll see what we're going to do with those in just a minute. Oh, my periods aren't showing it. Okay, so when you do a probability experiment and the outcomes are numerical, you can refer to them as a random variable. Okay, and that leads us into what a probability distribution looks like. So a probability distribution is a function, and there's your algebra throwback. Okay, we're back in the land of functions that maps each value of the random variables, and remember that's like these up here. Whoops, there they are. These up here. It treats these like the x's and then pairs each one up with its probability. So this one's going to be kind of a boring one because, I mean, rolling a single die is simple in probability terms, but under a probability distribution, you would have ordered pairs that look something like this. 1, 1/6, 2, 1/6. So I'm taking each possible outcome, each value of the random variable, and matching it up with what its probability of occurring would be. 5 1/6, and then 6 1/6. Okay, so again, when you're just rolling a single die, all of the probabilities are the same, you know, so that's why all of these numbers are the same. The big point to get here is that your x's are your possible outcomes and your y's are your probabilities. Okay, now a couple of things to keep in mind here that you should notice right away about this is your x's always have to be mutually exclusive. Okay, you can't have like any overlap. You're not working with intersections or anything like that. These are distinct outcomes. Okay, that's the only way you can make them a random variable is if you have separate distinct outcomes. And also, anytime you're working with a probability distribution, your probabilities should always add up to, because this is supposed to cover the entire sample space, your probabilities should always add up to 1. Okay, if they don't add up to 1, you don't have a true probability distribution because you're either missing a piece or you've got some overlap or something. But in order for you to have a proper probability distribution, you should have an overall probability of 1 when you add all your outcomes together. Let me just pause on that screen for just a second in case you're still writing down any of those words. So this here is another probability distribution, and you don't have to worry about like drawing this because you're pretty familiar with this already. This is the distribution of rolling 2 dice, okay? And if you look, each one of the bars, let me just find a color that's not going to blend in here, each one of the bars goes up to its respective probability. And they've converted them into decimals, but you'll see over here on the right-hand side, they've got everything listed there in fraction form too, which is what you're probably more used to. So again, these down here, these are your x values, and these are your values of the random variable. I'm just going to use some abbreviations here. Okay, so along your x-axis are your random variables, or your possible outcomes. Along your y-axis are your probabilities. And if I were to add up, you know, each bar's respective probability, my probability should add up to a total of 1. I know I'm scribbling all over this thing, but So again, this is just another visual representation of a probability distribution. Sometimes you'll see them in ordered pair form or table form. Sometimes you'll see them more graphically. In your book, they tend to favor, I mean, the bar graph method is certainly more popular in like statistics, but your textbook seems to like creating a, and I made these very big exaggerated dots, but instead of making like a bar graph, they make more like scatter plots where they just put a dot for each probability. Okay, and then they just show you that piece of it without the bars underneath. So there are all different ways that you can display this, but really the big idea is that you're matching up the possible outcomes with its respective probability like a function. Okay. Now, this particular distribution is an example of theoretical probability or a theoretical distribution. Okay, and let me show you what I mean by that. So over here in the corner, if I could draw your attention, theoretical probability. Most of what we've done so far in this chapter has been theoretical probability, and that's when you're calculating probabilities mathematically. So, like for example, all the probability problems we've been doing where we've said, you know, the number of favorable outcomes, the number of outcomes we like, divided by the number possible, or the whole sample space. Okay, that's considered to be theoretical probability. But there's also something known as experimental probability. An experimental probability is not, well, it's not theoretical. It's when you actually perform an experiment or when you actually look for outcomes and you calculate your probability based on how many outcomes you got of a particular type out of how many events or how many trials you did. Okay, so this is number of favorable outcomes, I guess you could say, but divided by now the total number of trials you did. Okay, so what that really means in this situation, because like I said, this is all representative of a theoretical probability distribution. Let's say that I actually sat down and rolled 2 dice, let's just do 10 times. That'll just make it easy, right? So let me make up 10 rolls of a dice real quick. Okay, so for the record, I didn't even make these up. I went online and found a 2 dice simulator and simulated the experiment so that all of my probabilities would, you know, be represented fairly. So if I rolled 2 dice 10 times and these were my outcomes, then what I can do is calculate each one as a probability out of 10 because I did 10 total trials. Just double checking. 8, 9, 10. Okay, so for example, my probability distribution might look something like this. Starting with 2, because that's the lowest possible one I could have. And my probability for that would be 1 out of 10, because I got 1, 2 out of my 10 trials. Next would be 3, and since I got none of those, that would be 0 out of 10. Okay, you can see where this is going. 4, I got 1, 2, 2 out of 10. 5, I think I got just 1 out of 10. 6, I didn't get any of those, so that'd be a 0 out of 10. 7, I believe I got 1, 2, 3 out of 10. 8, got none of those, 0 out of 10. 9, I got 2 of those. Oops, this was 10. 10, got 1 of those. And is that all 10? So I don't think I got any 11s or any 12s. Okay, and sorry that took a little long. Actually, we were all going to do that experiment in class, so this is probably shorter than doing that. But okay, so this is my experimental probability distribution. And you'll notice that the probabilities, I mean, they look representative. Like, obviously, 7s showed up more often than anything else. But these actual fractions or percentages are not equivalent to what was up here in our table. And that's because it was simply based on this one particular trial. So if I were to graph this, I might get a graph that sort of resembles this, but it won't be exact, okay? And that's what experimental probability is all about. Is it's not about theoretically what could happen, it's about what actually does happen. Now, what you're going to find is if I were to conduct more than 10 trials, if I were to conduct 20 or 50 or 3,000 trials of this experiment, the more trials I conduct, the closer and closer my distribution is going to be to taking on the same shape as the theoretical probability. Okay, I believe that's called the law of large numbers for my statistics friends. But you will notice that, I still have my random variables represented just like I did here. Okay, those are my x values. And if I went through and added up all of my probabilities, they should add up to 10 out of 10. Okay, or 1, because I'm representing all 10 of my trials. Okay, so that's it for theoretical versus experimental. There's just one more topic that we need to talk about here. So the last thing we need to talk about in regards to probability distributions is how to calculate expected values or mean values. And this is going to become part of a much larger statistics topic eventually. But for today, we're really just focusing on how to do this calculation. Okay, so I've written out here kind of in words how to calculate it. I think it'll make more sense once you actually see it being done. But if you take each random variable in a distribution, multiply it by its probability, and add them all together, what it's really telling you is what is the expected value? What do I expect to happen more often than anything else? Okay? Or what is the average of whatever things it is that you're looking at, whatever values of the random variable you're looking at. Essentially, what you're going to see is that it's really just a weighted average. Okay? So I'm going to shrink this up for a second and throw in a very high quality data set here. Shrink that, stick that up there. Okay, so here's a sample data set to work with. Again, I realize this is not the example that's in your notes. If you'd like to copy it down, you can. If you want to just follow along, that's fine. Maybe you want to watch this and then try the one that's actually in your notes. But so this, again, is a high quality data set. What I did, because it's late and I'm tired and I don't feel good, is I looked at the first 25 friends on my Facebook page and I counted up how many kids each one has. Okay, so I took the number of people who had that number of kids out of 25, converted each one into a decimal, and that's what you see here. So my values of random variable, my values of x here, these represent number of kids. Okay, so 16% of the people that I just happened to look at had 0 kids. Okay, that's what we're really saying here. And if you want to check my math real quick, these do all add up to a probability of 1, meaning I have covered my entire sample space. So let's suppose I asked you to find the expected value for this distribution. Okay, how many kids would I expect a random person chosen on my Facebook page to have? Okay, so what I'm going to do is I'm going to take each random variable, pair it up with its probability, and multiply them together. And then I'm going to add each one of those. So I'm going to multiply and multiply, multiply, multiply. And then I'm going to add these all together. Okay, here's what that will look like. So I'm going to go 0 times 0.16 plus 1 times 0.2 plus 2 times 0.28. I'll move down here, plus 3 times 0.24 plus, oh, I can't count tonight either apparently. My next one is 4 times 0.12. Okay, and then I'm just going to do that calculation. And I came out with a value of 1.96, which means right around in here, and probably closer to 2, is where I would expect most of the people that I'm friends with on Facebook to fall in terms of numbers of kids. Okay, so I would say that the average number of kids is 2, or the expected value of this probability distribution is awfully close to 2. Okay, but that's really all there is to finding an expected value, is it's taking, so first of all, you have to have random variables, which means that you have to have numerical outcomes. And you've got to be able to take that numerical outcome and multiply by a probability and then add them all together. Okay. Now, one thing I do want to point out, I gave you all the probabilities in decimal form. If these were given to you as fractions, so let's say I had something like, I'm just going to make one up real quick. 1 times 2/3 plus 2 times 1/6 plus 3 times 1/6. Okay, I don't know what this would represent. This is just numbers here. I did make sure that my probabilities add up to 1, though. So if I wanted to add these together, if I had a common denominator, which in probabilities you often do, and I notice I didn't do that here, but let's just make this a 4 out of 6, and then we should be fine. Okay. What you could do is just go through and do like 1 times 4 plus 2 times 1 plus 3 times 1, and then do the dividing by 6 because you're dividing everything by 6 at the end. And that way you don't have to type in the divided by 6 every single time. So again, that's just kind of off the cuff, but I know that you'll see that on your homework assignment tonight. So you may just, that might be a helpful tip for you. So, okay, that's all I have for you for today. Your homework is Lesson Master 7-6, okay, which should be up on the front table. And then also there is a book assignment that you are welcome to do on the back of the worksheet. And we will definitely revisit this topic tomorrow. So, thanks a lot. Have a great day, and I will plan to see you tomorrow.